Well, I'd like to thank you all and thank Dan for introducing the problem so well. And I'd like to thank Henry for the invitation to be here today. So I'm going to talk about what Dan talked about was using artificial techniques to split water and then use biological techniques to actually do the CO2 reduction. So I'm going to talk more about the water splitting part and what's involved in that, and in the spirit of this session to really reveal where physics has made a big impact and where more physics is needed. So before I start, I'd like to thank our sponsor, which is the Department of Energy Office of Science. I'm going to be talking about work that was mostly done in one of two centers, the Joint Center for Artificial Photosynthesis, which wrapped up its work last September, and a follow-on program called Liquid Sunlight Alliance, which is now taking some new directions. And on the right here, you'll see the institutional partners that are involved. Okay, so we've heard very nicely from Dan about the natural photosynthetic paradigm. And what I'm going to talk about today is how you kind of get from here over to here into these artificial systems, what's involved in building them, what you have to consider. Dan talked about the Z-scheme, but from a little bit different perspective than I will. The Z-scheme, so-called, is the energy Z, like so, involved in creating ever higher energy pathways to chemical reactions. And the scheme itself is quite complex. There's a whole bunch of different steps to it. And this is all organized by placing these bodies inside of a membrane. So the paradigm for artificial photosynthesis is really quite similar. The idea is that you have an ability to promote electrons to an energy level that is suitable for driving the chemical reactions that you want. And in the simplest embodiment, this is done by back-to-back semiconductors where light will be transmitted through them. You'll have a junction at the middle that will serve to create the fields that will split the electrons, driving split the charges, driving electrons over toward the reduction side over here, and the holes over to the oxidation side as shown here. And these are the band edges of these, and their band gaps are actually quite critical to get right in order to do something even as relatively simple as water splitting, which is what the role of photosystem 2 is. So why do we want to do this? Henry talked about the more immediate need of efficient use of efficient ways to recycle carbon beyond simply making biomass and directly converting it. If you think about where we are right now, we can build electrolyzers that you plug into the wall and do a lot of the chemistry that we're talking about, simple CO2 reduction reactions, water splitting reactions. These have the advantage of making dispatchable products, so they're things that you can make in one place and take somewhere else, but they really have to be attached to the grid. Nonetheless, they are a way of storing chemical energy from renewable energy sources such as photovoltaics and wind sources, which are necessarily intermittent. So the interest, of course, right now is from the sponsors that have, are willing to spend a lot of money because this is not really even a technology and certainly not an industry yet. So space, there's been interest from space, military industry, and also some thinking about high margin products that can be made this way. Way in the future, the vision is that if we really learn how to do it right, just as you can put a tree in your yard, you can put a local energy system that would produce some kind of fuel that would be useful to you next to your home and have it available, working as a modular and deployable source. And most importantly, it would not have to be grid attached. So future here is who knows when, but the science in order to get there will help make all the rest of these earlier applications much better. All right, so I'm going to talk about water splitting primarily right now, and the integrated photoelectrochemical hydrogen generators, there are a whole bunch of them that have been published, and all of them have better than 12% solar to hydrogen conversion efficiency. Here's some photos of arrangements that are on the back and the references. All of these have very specific elements in them. So if you think about them, the main components are a photoabsorber, something that will absorb sunlight and make electrons and holes. The holes will be swept over to the anodic side. The anodic side is where you will drive reactions like water oxidation. The cathodic side will be where you will drive the reduction reactions such as generation of hydrogen or carbon dioxide products. And you have to have a membrane separator in between. This is especially important because if you allow products to freely float around between these two elements, you will get a significant back reaction, which will cause a big hit in efficiency. However, there's, as I will talk about at the very end, there's a lot of issues with how to do this exactly in a way that's really efficient. Now, there are a number of different embodiments that you can think of for these components. One is the purest one, which is basically where the photoabsorber does all the work, and it has an anodic side and a cathodic side natively through its material, and then off to the side you'll have a separator. You can have an embodiment that is probably more common, and certainly these pictures here are for that implementation, which is a photoabsorber that is physically sandwiched between an anode and a cathode that are contacted to it for maximum electron transport. And again, a membrane off to the side in this architecture. And then finally, a PV electrolysis device where the photoabsorber can actually be quite distant from the anode, the separator, and the cathode, so this part. Or it can be physically contacted to it with these guys out off to the edge. So all of these have been demonstrated in one sort or another. These two bottom ones are the more common ones that you will see in the literature. So where does physics come in here? We've been talking so far a lot about chemistry, but I want to focus on the important physics that has to be done to do this right. Of course, there's semiconductor physics because the photoabsorbers are semiconductors in order to generate the electrons and holes. But also there's a very important role for optical physics, for surface and interfacial physics, materials and solid state physics, and polymer physics. These are the more active areas. This one maybe is not as active as it should be, I would say. Fluidics and thermal physics are also really important. If this box that this is contained in is full of a liquid electrolyte, it doesn't have to be, it can be vapor or a solid state electrolyte, but if it's full of a liquid, you're going to be making a lot of bubbles. And those bubbles have very important consequences for how things work inside of these systems. Also, as Dan alluded to, you're not going to be getting much more than about 20% solar to chemical energy efficiency just due to the limitations of the photoabsorber. However, that other 80% gets lost to heat. And what does that heat do and where does it go? These are things that actually haven't been studied well enough, in my opinion. So let's start with the semiconductor physics. So you have your semiconductor, they're back to back, you have a junction, they separate charges, and this is all well and good, but there's important constraints here. One is that you need at least a 2 electron volt photovoltage to really make this work well. And that's true even for water splitting. Water splitting can get away with a little bit less, but for CO2 reduction, you absolutely need the full 2 volts. So this means immediately that you're never going to be dealing with a single material. You're going to have to be dealing with multi-junction semiconductor stacks, which have to be designed so that all of the band gaps and the energy level alignments are what you want them to be. So this is one big tall order, and right now the only stacks that we have that are really worth it are the 3-5s, so gallium arsenide family. Now, once you put these together, there are 2 things that happen. One is that you have significant efficiency losses due to recombination of the charge carriers, and the other is you get a lot of corrosion. Anytime you send, especially with holes, anytime you send holes out to the surface here, you're going to be competing between a chemical reaction that you want and one that you don't want. So you need to have all of the band gaps actually straddle the potentials of the reactions that you want to drive. so that either of the stack itself or of the pure material. And this shows you immediately the problem that there are very few materials that actually have the right band gap and also the right band edge alignment. TiO2 has got the right stuff, except it's basically transparent and visible, so it's not a good solar absorber. Cuprous oxide is a good photo absorber, has band edges in the right position, but it corrodes like crazy. So this is here the challenge that we are currently dealing with. So how do we meet this challenge? Well, we try to find new materials. Finding new materials randomly is extremely difficult and very time consuming. So we've tried to accelerate things a little bit by using high throughput theory from the materials project in order to do screening of large databases for materials that might be good candidates. Screening on the basis of their stability, their susceptibility to corrosion, whether they've got the right gap and the right structure, and whether their band edges are aligned in the right place. And going through this, this exercise, we actually found 43 new potential CO2 reduction photocathodes. So Dan emphasized how nature does all its CO2 chemistry in the dark and is organized that way. The thing you can do with artificial systems is actually have the potential of driving the chemistry directly from a photocathode, and that is one thing that we are interested in seeing what its feasibility is. So having this sort of thing in hand, how do you learn about these new materials? Well, this is where, of course, our rich tradition in optical physics and electronic structure theory become very important. But we can also add new tools such as machine learning and artificial intelligence in order to take data from large libraries of materials that have been made in parallel processes and whose optical properties have been measured in order to be able to predict compositions that might be more advantageous. We also can get deep understanding in these new materials for their photocarrier dynamics, for how electrons are transported across interfaces, and also for how they deal with polarons. Now, polarons I'm going to talk about in the next slide, but this is one of the things that kind of comes along with the challenge of having multi-element semiconductors that have got advantageous band gaps and corrosion resistance, is that they often have disadvantageous properties for electron transport. So I'm going to give just one quick story, which is about bismuth vanadate. Bismuth vanadate is a material that has been widely studied. It doesn't have a very good photovoltage, but it can be made reasonably stable and is been used for a water oxidation photoanode. It has two types of polarons. Now, polarons are basically things that get in the way or deal with localization of charge carriers in the matrix. In small polarons, in the case of bismuth vanadate, are due to trapping of charge carriers on vanadium ions in the lattice. And the consequence of this is that the mobility of the charge carriers is really low, and which means that they can't travel very far from where they're born, which means you're very inefficient in using light. Large hole polarons, on the other hand, are due to long-range distortions due to vanadium vacancies inside of the matrix. And it turns out that these can actually be beneficial for mobility by creating advantageous transport channels. And you can use dopants in order to change the distortion and change the conductivity, and also to manage electron hole recombination losses. So learning how to manage polarons, learning how to live with them through advantageous composition of these multi-element semiconductors is a very active area of research. Okay, so another thing that we have to think about is what happens when we want to use a catalyst in this sandwich geometry, like I'm showing right here, where you put a catalyst on top of the semiconductor and shine light through it. In this case, the light just goes down to the bottom. We have an opaque catalyst at the back where you don't care anyway. So what happens out here when you try to shine light through the catalyst? Well, it turns out that if you manage the optical properties of these layers properly, you can actually get a very efficient light transfer through them. and optimize the efficiency of the solar to hydrogen conversion, which in this device was shown to be near theoretical, which is 19.3% solar to hydrogen. And the way that's done is by making the rhodium particles really small, about 10 nanometers. And it was shown that their absorbance drops to a very low value at this size. And also having the TiO2 be at a suitable thickness to act as an anti-reflection coating. So if you get the two together, you can actually gain 4% in efficiency just through management of the optical physics alone. But you can do more than that through taking advantage of photonics by creating cones, if you will, of a dielectric on top of the semiconductor and using those cones to channel the light through really effectively. So in this case, we're looking at nickel, which is a water oxidation catalyst, or copper, which is the most useful carbon dioxide reduction catalyst, a thin film catalyst. And these experiments and simulations have shown that by having these cones present on the surface, you can take advantage of the photonics and get very good light transmission, even though these layers are fully opaque and continuous. And the current potential curves bear that out here. But we can go a little further even and think about plasmonics, because one of the interesting things about nanoparticles is that they have plasmon transitions at various wavelengths, which is what gives the solutions their colors. And one of the things that has been done is to take advantage of that to build a highly miniaturized solar water splitting system, which consists of a gold nanorod, which is right here, that has a cobalt oxide catalyst, which is on the side, and platinum separated by a layer here, TiO2, and then platinum nanoparticles on the top. Now, it turns out that in this arrangement, the platinum nanoparticles actually undergo plasmon-induced resonant energy transfer. And this is very advantageous for being sure that even though the surface area is really tiny, you get maximum transmission of solar excitation, much better than you get through scatter. There's also a possibility with these nanoparticles of having hot carrier injection. And what hot carrier injection can do is, even if you have band edge alignments that are not advantageous, if you can generate hot carriers, you can actually drive chemical reactions that are out of range of the band gaps themselves. Now, this has been demonstrated. It's unfortunately very inefficient, but this might be a direction to improving efficiency in these artificial systems. Okay, I'm going to move on now to talk a little bit about the anodic and cathodic surfaces, and specifically I'm going to spend most of my time on the cathode. So the oxygen forming reaction happens on the anode, so this is like photosystem 2. The dark processes that take place in nature take place on the cathode in these systems. That is hydrogen formation and then CO2 reduction. And Dan showed you that you actually need a lot of photons and a lot of electrons and a lot of protons to build anything that looks like a useful carbon chain. But something that people don't think about very much in this, in that a lot of the effort has been to try to make this selective, to have the reaction stop at a suitable point to make the product that you want. There's actually another issue which has to do with the interfacial physics involved with these materials. And I'm going to talk here specifically about copper. Because this one is one that's been best studied, but this is likely to be going on in a lot of situations when you're dealing with thin film catalysts of this sort.
Can I give you a 3-minute warning?
Okay, thank you. And so with what we've seen is that there's dramatic reconstruction of these catalysts. And in this reconstruction process, you can actually lead to improved selectivity, even though you are destroying the perfection of the surface. And why this happens and what the physics is involved is actually completely unknown. How this happens, it can be looked at in real time, and this is experimental work underway, where you are looking at CO2 reduction in situ using grazing incidence, electron, X-ray scattering, and X-ray absorption spectroscopies to follow within a 2 nanometer thick region how these materials transform, and that might give us some clues. I want to just wind up a little bit with talking about membrane separators. Now, ideally, these membrane separators will block products, have low ion transport resistance and be very stable, but actually, we haven't found materials like this at all. And one of the big issues is that the crossover and ion transport resistance are actually coupled, because crossover is, ion transport requires a lot of water inside of these membranes, and that also facilitates product crossover. And this is something that is an unsolved problem. And finally, I'd just like to say that the polymer physics definition of membrane permeability, which we understand as being due to fluctuations in the polymer chain, which control diffusivity and solubility, are only worked out for steady state, and it's only worked out for single permeance. We never have that situation in solar fuels. We never have anything that looks like a steady flux of anything. Sun goes up, sun goes down. The potential changes of product mix changes. Exposure to carbon dioxide causes plasticization. Things dry out, things rehumidify. All of these cause continual changes in the polymer, and we don't have a theory to deal with that yet. So I've tried to lay out some areas where semiconductor physics, optical physics, surface interfacial physics, polymer physics are important to the function of artificial systems. I just want to leave you with the thought that this ties back to what Dan said, is that going from here to these very simple constructs at the component level is really not where we want to be. We're not getting the efficiency, we're not getting the performance that we really need, and there's a lot of underlying instabilities we have to deal with. So more and more the field is moving toward something that is more biology-like, where we think about how to use physics and chemistry to directly manage the catalytic process itself. Thank you all for your attention.